Hello again, and welcome to part 2 of our video lectures on Chapter 3. In this part of the lecture, we'll look at motion on a ramp or sloped surface. We'll be looking at some examples with a bicycle riding up and down a slope, and also a skier sliding up and down a slope. So motion on a ramped or sloped surface, the way we're going to analyze this is by using a little trick. We normally orient our x and y axis with the x-axis pointing horizontal and the y-axis pointing vertical. What we're going to do here is we're going to actually tilt our coordinate axis along the sloped surface. So our x direction is going to point up or down the slope. Depending on the angle of this hill or ramp here. And then, of course, the y-axis is perpendicular or at 90 degrees to the x-axis. So it's going to also be at an angle like this. The next thing we're going to do here is really the key thing, and we're going to determine the acceleration due to gravity along the sloped surface. So if we consider our skier here, for example, skiing down the slope, normally, well, always, gravity points directly straight down. So our gravity acceleration vector, which is 9.8 meters per second squared, is pointing straight down towards the center of the Earth. But the skier, of course, is not moving straight down. The skier is moving along the slope. So the trick here is to decompose this acceleration due to gravity vector into its components. One component that we're going to use is this one that points down along the slope. The other component, which is shown here, we won't be using in this chapter, but we will use this later on in the course. But for now, the key thing is we want to find the x component of our gravitational acceleration vector. And one of the other tricks here is to notice that this triangle here, shown in red, is also a right triangle, just like our ramp is a right triangle, and they both share the same angle theta. So this slope that the skier is on has some angle theta. This angle here will be, and you can prove this using some basic trig that we're not going to do right now, but these two triangles share the same angle. So therefore they are similar triangles. So the idea here is this downward acceleration due to gravity is going to be g times sine theta. Now we can get that from this right triangle here. Remember that this, if this is theta down here, this is the opposite side of the right triangle. This is the adjacent, and of course this is the hypotenuse. So the opposite, which is a sub x, is equal to the hypotenuse g times sine of theta. So for all these problems with motion on a ramp or slope surface, we'll be using an acceleration down the slope equal to g sine theta. And we can also kind of just do a check here. Notice if the angle theta goes to 0, all right, in other words, there's no slope, then the skier is just sitting on a horizontal surface, and obviously he or she is not going to go move at all due to gravity, because now you're on a flat surface. So the acceleration would be 0. And remember, the sine of 0 is 0. On the other hand, if this slope gets steeper and steeper until it's actually a vertical drop, then we have theta here is going to be 90 degrees. And you'll remember from math class that the sine of 90 is 1. So in that case, the acceleration of the skier is just equal to g, which makes sense. The skier would then be in free fall. He or she would just be falling straight down. So this formula works for any angle between 0 and 90 degrees. All right, so our equations of interest that are going to help us solve problems here are the standard kinematics equations that we learned about in the previous chapter. And all we have to do is remember that the acceleration in these equations is given by this, g times sine theta. So this is the formula for figuring out final speed. It's just equal to initial speed plus the acceleration in the x direction times delta t times the time. And again, this a sub x is given by g sine theta. This is the position formula where the final position is equal to initial position plus initial velocity times the time interval plus 1/2 a delta t squared. And which is often the case in this formula here, usually a lot of times we're going to start from the origin. So x of I is going to be 0, and we're going to start from rest. So v sub I is going to be 0. So in that case, we can write this kind of cumbersome position formula into a much more compact and convenient form. The distance that something moves down the slope, that's d, is just equal to 1/2 a t squared, where again a is actually a sub x, that is our g sine theta here. And then if we don't have any time information, this is the useful formula where the final velocity squared equals initial velocity squared plus 2 a sub x times delta x, which is the displacement. So let's go ahead and work through some examples to see how to do this. So our first example is a downhill speed skiing competition, and it has a course with a slope of 30 degrees. So you can see here, we'll model this, this race as if this skier was on a slippery ramp here, and we're going to assume no friction or wind resistance to make this problem much easier to solve. The other thing we're told here is that the distance from the starting gate to the finish line is 100 meters. So it's a very short race, basically around a football field. Starts up here, gets to the bottom 100 meters farther. So two questions here. Part A, how long does it take the skier to complete the race? And part B, how fast is the skier going at the finish line? So for part A, how long does it take the skier to finish the race? Well, we can use our simplified position formula, d equals 1/2 at squared. Remember that a is equal to g times sine of theta, where the angle of the slope, theta, is 30 degrees. The sine of 30 turns out to be exactly 0.5. So we multiply that times 9.8, which is g, and we get our acceleration down this slope is 4.9 meters per second squared. So we know our distance is 100 meters. And so that's equal to 1/2 times 4.9 meters per second squared, that's our acceleration, times t squared, and t squared is what we're solving for. So 1/2 of 4.9 is 2.45, so I went ahead and did that step there. And finally, we can solve for t squared here by dividing 100 meters by this number here, 2.45. So finally, to get t, let's take the square root. So t is the square root of 100 over 2.45. So you can tap that out on your calculator and you'll find the time to be 6.4 seconds to get down the slope. Part B of this problem asks how fast is the skier going at the finish line? So here we actually have a couple different ways to solve this. Remember, we saw this in the last chapter. There are often more than one way to get to the solution of some of these problems. So let's look at a couple different ways how we can solve this. So the final velocity, remember, is equal to the initial velocity plus the acceleration times the time. So we know that he's starting from rest, so that's 0. That's our v sub I, the initial velocity is 0. The acceleration from the previous slide was determined to be 4.9, and the time was also found in part A of this problem, was found to be 6.4. So our answer is just 4.9 times 6.4, which is 31.3 meters per second. Now, the other way to solve this is we could use the equation without time in it. If we hadn't done part A first, this would probably be a little bit easier. The final speed squared, which is what we're solving for, is equal to the initial speed squared, which by the way is 0, plus 2 times the acceleration times delta x, which is the distance he travels. So 2 times a, remember a is 4.9, and the distance, delta x, is 100 meters. That's how long the race was. So our square of our answer is 2 times 4.9 times 100, which is 980. But remember, we have to take the square root to get our final velocity. So the square root of 980 is the same answer as we got up here, 31.3 meters per second. Let's now look at another example with motion on a slope or a ramp. In this one, we're going to look at an example of coasting uphill. So let's say you're down here riding your bicycle on a level road, and you're riding at 10 meters per second, and you see this hill up ahead, and all of a sudden your bike chain breaks, right? And we're also told this hill has an incline of 10 degrees. So your bike chain snaps, so obviously you can't pedal anymore. So all you can do is coast as far as possible up the hill. So we want to find out how far up the hill do we get, and also what is the maximum elevation you obtain. In other words, how high up off of the original altitude down here do we end up? And then part C is how fast will we be going if we coast back down to the bottom of the hill. In other words, we coast up to some point, we stop, and then we turn around and we accelerate back down. How fast are we going to be going at the bottom? All right, so let's go ahead and answer these questions. So for part A, how far up the hill does your bike coast? Well, notice again, we don't have any time information. We don't know how long it takes to get to the top and so forth. So we can use the equation that doesn't have time in it, which is very convenient. So the final velocity squared equals initial velocity squared plus 2 times the acceleration times the distance. Now remember that the acceleration here is going to be g sine theta. However, we have to be a little careful here. Remember that this bicycle is going up the hill. So if we call this our positive x direction, the direction that she's coasting in, then the acceleration is obviously going to be down the hill, right? The gravity always works down the hill. So the acceleration in this problem is going to be minus g times sine of theta. Okay, so sine of 10 degrees is 0.174. We multiply that by negative 9.8 to get negative 1.70. So that is our acceleration. Now think about this problem. When this girl here coasts her bike up the hill, when she gets to the final resting place here, her final velocity is 0. So this term here on the left, her final velocity is 0. Her initial velocity was her speed down at the bottom of the hill when her chain broke, and that's 10 meters per second. And remember to square that there. All right, so our equation says 0 equals 10 squared plus 2 times negative 1.7 times the distance delta x, which is what we're going to solve for. So 2 times negative 1.7 is negative 3.4. So I did that step there. And then to solve for delta x, we can basically move this whole term over to the left side, and we lose our minus sign, which is nice. So delta x ends up being 100, this number, divided by 3.4, which is 29.4, and the units, after all these cancel here, we end up with 29.4 meters. So she has coasted up the hill a distance along this x-axis, a distance of 29.4 meters. Part B of this problem asked, what is the maximum elevation gained by your bicycle? So if you think about this just from a math or geometry perspective, she has coasted up this hill 29.4 meters. We want to know, what is this height here, h? Okay, so we've got a right triangle here. We know this angle is 10. We know the hypotenuse is 29.4. All we have to do is find this side here. Remember, this is called the opposite side of the right triangle because our angle is over here. So using right triangle trig, the sine of theta, the sine of 10 degrees, is the opposite over the hypotenuse. The opposite is h. The hypotenuse is 29.4. Therefore, we can now solve for h, which is 29.4 times the sine of 10 degrees. So this is 29.4 times 0.174. And that turns out to be 5.1 meters. So that is her elevation gain, or her altitude now is 5.1 meters above the original height of the road down here. The last part of this problem asked, How fast will you be going if you coast back down to the bottom of the hill? So what we're talking about here is remember she made it up 29.4 meters up to here and she stopped. Now she's going to turn her bike around and coast back down. And, she's not pedaling, of course, right? She's got a broken chain. We're going to find out how fast is she going when she reaches the bottom here. So again, we can use our equation here without any time in it. So we don't have to solve for time. And so we've got final velocity is equal to squared is equal to initial velocity squared plus 2 times acceleration times delta x. Now this is the key here, the trick here. Our initial position was at the bottom of the hill. Remember, we're going to start the problem over here. She's going up the hill, stops, turns around, and comes back down the hill. So our initial position, which is down here, is the same as our final position. So the net displacement of the rider is 0. All right, if she starts down here and ends up down here, she basically hasn't gone anywhere. Her delta x is equal to 0. So this last term in this equation is 0 because delta x is 0. So we can just ignore this last term, and all we've got here is that the final velocity squared is equal to her initial velocity squared. And of course, her initial velocity squared was 10. So, technically we have v final squared equals 10 squared. So if we take the square root of both of these, we see that her final velocity is plus or minus 10 meters per second. Remember, whenever we take a square root, we always have a plus or minus in front of our answer because either one will work. However, from that works mathematically, but from a physics perspective, we know that she's going back down the hill, so we choose the negative answer. Her velocity is going to be negative 10 meters per second because remember, x is pointing up the hill. That's our positive direction, so her velocity is in the negative x direction. And some of you maybe realized, and there's another way to solve this problem that we really haven't learned yet. That is, her speed coming down the hill is exactly the same as the speed was that she went up the hill. And the reason for this has to do with the conservation of energy principle, which is something we'll learn about later in this course. The last thing we're going to do in this part of the lecture is a demonstration that shows kind of a nifty way to measure the acceleration due to gravity with a cart on a ramp. So recall in the previous chapter, we estimated the value of g, which of course is 9.8 meters per second squared. We found that out by I dropped a tennis ball basically, and we timed how long it took for the ball to fall to the ground. We did several trials, averaged the times together, and we came up with something very close to 9.8. We were within about 2% of the correct value. Well, this is a different method of measuring g. We can use what we've learned here in this part 2 of the lecture here on motion on a ramp. If we have a cart or a car that rolls down a ramp, let's let the distance that it rolls here along, the ramp surface here, we'll call that d. So remember that distance traveled is 1/2 a t squared, and a, remember, is our acceleration due to gravity going down the ramp. But of course, a is not equal to g. A is equal to g times sine of theta. Now there's a little trick here. Instead of measuring this angle, which is sometimes kind of difficult to do in the real world, especially with small angles, we can use trig to figure out our angle. Remember that the sine of theta is equal to the opposite over the hypotenuse. So here's theta. Our opposite is the height of the ramp over here. So that's h. And the hypotenuse is this part of the ramp up here, the long part, which is just the distance that the cart is going to roll down. So, so sine theta is equal to h over d. So our acceleration is equal to g times h over d. So I'm going to plug all of this here, g times h over d, into this our distance formula up here for a. and I get d, distance, is equal to g h t squared over 2d. All right, now our goal here is to measure g, the acceleration due to gravity. So we can solve this equation here for g, and it's shown here in the box. The acceleration due to gravity is equal to 2 times d squared over h times t squared. So what we can do is we can measure d and figure out how many meters this is. We can measure h, that's the height of our ramp vertically here, and we can measure t, the time, with a stopwatch to see how long it takes this cart to roll down the ramp. So let's go ahead and watch the demo and collect some data. So what I have here is a very simple ramp. It's just a board that's propped up here by another board. And we're going to roll this little toy car down the ramp and time how long it takes to go down here and see if we can use this data to calculate the acceleration due to gravity. So there's a couple measurements here. You can see I put a piece of tape here on the board that's 45 inches from the bottom. We'll convert that to meters later. The other measurement is that the height of the board, we're right here at the starting point, is 3.25, 3¼ inches. We'll also convert that to meters. So let's go ahead and take some data with our little car here. I'm going to use my stopwatch on my cell phone again. All right, so our first measurement is 1.85 seconds. We'll do a couple runs here and average the results later. .74 seconds. .86 seconds. By the way, this is another good use of a ping pong table. The ping pong net is actually catching the car down here. All right, let's do one more here. 1.75 seconds. That should be pretty good. We'll go with that. So we saw in the demonstration that the distance of the ramp, the board basically that the little car drove down, was 45 inches. And I converted that to meters. That turns out to be 1.143 meters. And furthermore, the height of the ramp where the car basically started was 3¼ inches, which is 0.08255 meters. So these are the values for D and H that we're going to plug in here. The other thing, of course, is the time. So in the demonstration, you saw that I actually did the experiment 4 different times. That's always a good idea to do multiple trials because of to try to eliminate as much error as possible in measuring the times. So these were the 4 times. We had 1.85 seconds, 1.74, 1.86, and 1.75. So if we add all those together and divide by 4, we get an average time of 1.80 seconds. So that's what we're going to plug in down here for t squared. So our estimate for g is 2 times 1.143 squared over 0.08255 times our time 1.80 squared. And amazingly, this turns out to be 9.77. And so if we round this to 2 significant figures, we get 9.8 meters per second squared, which is exactly the result we were looking for. So this kind of gives us a little more confidence in all these formulas and so forth for dealing with motion on a ramp. We can see that it very accurately allows us to determine and calculate the value of g, the acceleration due to gravity. I hope you enjoyed this lecture, and we'll continue on with part 3 next.